All right, in this video, we're going to be doing some more Lenz's Law practice because if there's anything I know, students cannot get enough Lenz's Law practice. It tends to be one of the tougher concepts in this course. Everyone's like, oh, I love the concepts with no math, right? Then they hit Lenz's Law and they're like, oh, wait a second, I take that back. Give me some equation that I can plug and chug into. But I'm going to try to make this as easy as possible, okay? So at the end of the slides, you'll see several new Lenz's Law examples, one of which is this question, which says, what will happen to the induced current if we do different things to this magnetic field that is inside? Once again, this magnetic field is into the board, and this loop of conducting wire likes this magnetic field going into the board. It's enjoying that, right? So the question is, what will be the induced current in this loop if the B field is increasing? So we have more B field going into the board, right? We have more B field going into the board. What will be the induced current? Well, if there's more B field, it's like, I don't like that. I liked it better when I had just this nice, cozy, perfect amount of B field. Now it's too much for me. So it wants to induce a magnetic field or a magnetic flux inside the loop that opposes the increasing magnetic field this way, okay, going into the board. So it wants a flux this way to oppose this increasing magnetic field going in, all right? And so what direction of a current will give you a magnetic field coming out? Well, if I have my thumb going in this direction, then my fingers will wrap around and come out the back and out towards the viewer here in this case. So this would be here, and counterclockwise induced current would end up giving you a magnetic flux coming out that opposes an increasing magnetic flux into the board. Okay? What would happen B if the B field is decreasing? Well, in that case, we'd want to get that B field back again. So it'd be just the opposite situation. You just change the direction of this current. And what would happen if the B field stayed constant with a B field of B0? Well, if nothing's changing, the little loop is happy and nothing wants to change, okay? And it doesn't want to induce a current. So if B field is constant, there's no change in flux, that means the induced EMF would be just a 0. Okay? That's that example. All right. In the next example, we have kind of this little funsy situation here where we have a long straight current carrying wire, right? So imagine that I have a long straight current carrying wire here, I, right? And so if you have this wire, that means that, magnetic field is going to be going into the board on the bottom. So that's X's here. And then coming out on top, right? In, around back, and then at the top, it's going to be coming out towards you. Okay, so we got a couple things going on. First of all, we have one loop called A, right? That's doing this. Now, remember, there is a magnetic field, the magnetic field lines coming out of here, right? They're like these little loops here. Go like this, and then come out like that, right? They kind of look like this, and they get weaker and weaker the farther away you are, right? And the reason for that is this equation, right? The B field due to a long straight wire over 2 pi r. As r gets bigger, right, this distance away from the wire, then the B field should get smaller. Right? They're inversely related to each other. So if the B field gets smaller as I pull this away, then this loop is going to try to induce a current to get that B field back again. So it wants more B field coming out. It wants more B field coming out, right? And so a B field coming out would go in around here and out the other side. That would be a counterclockwise current. All right, this current here will give me more magnetic field coming out because as I pull this away, I'm losing magnetic flux coming out, and it wants more of it to make up for what it lost, right? We have this other case of B, right, where we have this being pulled away. Once again, it's losing magnetic field, but it's losing magnetic flux into the board, and it wants more magnetic flux into the board again. So what current will induce a magnetic flux in? Well, that would be a magnetic field. That would be a current this way that would give a magnetic field in, that would wrap around and come out on the outside. So that is a clockwise current. Okay? Once again, remember, this is only going inside the loop, and as it comes around the outside, you're actually going to have these magnetic fields coming out at you, but that doesn't matter because we only care about the flux through the loop. Okay? Now, in the case of C up here, you're being pulled laterally. Okay? It's a little bit different. You're being pulled laterally. In this case, R stays the same the entire time, which means B field stays the same. If B field stays the same, there is no induced current and the little loop stays happy. Okay? All right. Next, we have D, where that's pulled towards the wire. We know right away already that this is going to be the opposite case from B, right? Because we're just the opposite things happening. So we can predict automatically that the current here in this case is going to be counterclockwise, but let's see why that would be. Okay, why would that be? Well, so if R is getting smaller, B is getting bigger in this case. So R is going down, B is going to get bigger. That means we get more and more B field moving through here, this loop, which means more and more flux. It doesn't like this new flux, so it wants to oppose it by creating a magnetic flux coming out inside that loop. Well, what will do that? So if I have a current going this direction, it'll wrap into the board here, come out the other side. So that'll be a flux that comes out here. And so that's going to be a counterclockwise current. Okay, that is Lenz's law. I have one more example in the slides here for you to practice. And once again, these are problems that you can find anywhere. On online textbooks, just Google Lenz's law problem. You can find a bunch. And it's the sort of thing where it's a lot like those little 3D pictures. I don't know if you've seen those before, but like you kind of like stare at them and like cross your eyes for a little while, and eventually, the image pops out. I feel like Lenz's law is a lot like that. It's hard to see it originally, but once it makes sense, it clicks, and you're like, okay, I can do any Lenz's law problem ever. So wait till you get to that point. Keep practicing until you get to that point. If you need a little help getting there, I'm always here to help. All right? Okay. Good luck.